Okay, so calorimetry and specific heat is the topic. I'm going to go through many of these slides pretty quick at first so we can kind of get to the heart of what we are doing here. All right, you guys remember this? Endothermic, it's good, friend. Exothermic, you do. You guys have already learned this stuff. This is just review that this is part of, or at least related to, what we're kind of going to do next. The key to this is, when we first learned this, you just saw these equations. You just saw these graphs. Hey, here's what happens with reactants and products and activation energy. We just gave you this. Kind of, here's what it is. How do we measure that? And that's where calorimetry comes in. If you see that set up there on the left, that is what we are going to construct tomorrow. You are going to do a lab where you try to do exactly this, and we are going to make some measurements of temperature with the thermometer. We're going to heat up some water inside of a pop can, and we are going to make measurements similar to what you guys saw on the gizmo, but this is what we're going to actually do tomorrow is some calorimetry. Right, where we're working with heat. But again, what we can actually measure, right, is the temperature change of the water. That's the key to a lot of this, is how much change in temperature do I have? Because how do you change the temperature of water? What do you have to add to it? Heat. Right? And if the temperature goes down, same thing. We didn't add heat to it, heat left the water. But that is essentially how we are going to do this tomorrow. We're going to have a setup that looks something like what you see here on the screen. Nope. So again, the trick with the calorimeter is we try and do some kind of controlled thing. And what we're going to measure is the change in temperature of the system. And that's what we're doing with the thermometer. A lot of these that you see are insulated because, again, we want to measure the temperature of whatever process is happening here, not necessarily the influence of heat on external things like the heat of the room, any kind of light or anything else that is going to impact the amount of energy going in or out of this system. Everybody got it? I will post these notes later, so you'll have these in case you missed it. So this is a review from physics. For those of you that had physics, again, this is something we've used in this class. We've measured and used joules. But I don't know that in chemistry we ever really talked about what joule is. Joule is what we use for measuring heat. Less specifically than heat, joules is a measurement of energy in the metric system. And a joule is 1 Newton of force over the distance of 1 meter, which is not a lot of energy. If you remember in those equations that we did for like combustion, we were not using joules, we were using kilojoules. I think for some of those combustion heat reactions, when we were doing endothermic, exothermic, and heat inside of stoichiometry, we were using kilojoules.
Yeah, what kind of calorie are we talking about?
Like we're not talking about
We are talking about calories in food. But what you have in food is actually a kilocalorie. They just shorten it for the sake of the energy in your food, which we'll talk about in a moment. But a calorie, more generally, the real definition of an actual calorie is the amount of heat required to raise the temperature of 1 gram of water by 1 Celsius degree. How much is a gram of water? Not a lot. Several drops is a gram of water. Moving 1 gram of water 1 degree Celsius, is that a lot? No. And in 1 calorie, which we just said isn't a lot, there's 4 joules. So again, a joule is not a very large amount of energy. Right? But this is how we measure the amount of energy to raise the temperature. 1 gram of water, several drops, by 1 Celsius degree, not very much of a difference, is how we define 1 calorie. I'll let you guys get this into your notes. We're kind of all done. All right, so specific heat is the next thing. So here's your definition for specific heat. No, do not write this whole chart, but I would write that top thing. The amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. And now this is a property of these substances. Specific heat of water, ethanol, other types of water, a bunch of different elemental solids or liquids. What does it mean that the difference between water and gold is so great? Water is 4.18. Gold is 0.129. What does that mean? How would you tell me that in plain terms? Easier to heat up. What do you mean? Anything's easy to heat up. Just put it on a stove. That's easy.
It takes more energy to heat up water.
Ah. This is the heart of specific heat. Okay? When you put a pot of water onto the stove and you turn the stove on high, how long does it take to bring that water to boil? 15? 20 minutes? Bruh. Yeah, your stove is broken. Call a maintenance technician. Your stove is broken. But we're going to get to that. Let's say it takes Ethan 20 minutes to boil water. How long does it take you, BK? 10 minutes. Let's call it 10. Let's call it 10. But here's the brain teaser. Well, let's say it's the same pot of water, okay? On your stove, takes 10 minutes. Your water starts at the same temp, let's say 18 degrees, right? Is tap water temperature, room temperature or so, a little less than room temperature. So if your water starts at 18 degrees, your water also starts at 18 degrees. What's our target temp?
212 Celsius. 100.
Take your time. 100 Celsius. So we're starting at 18, we're going to 100, and it's the same amount of water. You're both putting 2 cups of water on there, right? Whatever you're supposed to boil for mac and cheese. Now,
If do people put salt in water?
they do. It's complicated. It changes the boiling point, and it also adds, it changes the boiling point of the water slightly, but also flavor.
Does it make the boiling point up or down?
I don't know. I have to look. I think it makes it. I don't know what that does to the IMFs for water. I'd have to look at that. Said we're gonna learn later this month.
Is there a difference when you have a gas stove or if you have electric? Like how much heat it will add?
Okay, we'll talk about that in a second. Let's pretend for a moment that you guys both have the same stoves. Okay? You have the same water, the same pan, the same everything else. You boiled your water in 10 minutes. You boiled your water in 20. What was the difference? How, though? There's the same stove.
You crank that.
Yes. So you set your stove to 9. Ethan has more time. He set his stove to 5. Right? But ultimately, is there a difference in the amount of heat that we added to those 2 pans? No, it's the time. It's how much heat was coming out of the burner. But ultimately, it's the same amount of heat. Can we agree that it's the same amount of heat to change the water from 18 to 100 degrees?
It's gonna need more
Same amount of heat.
than
But
Same amount of energy to get the water to boiling.
You're adding more. Like, not like it's still the there's the same temperature on the heat.
The burner would be larger. It would be doing different heat. Remember, heat and temperature, are those the same thing? No. Right? So the flame on both of your stoves, were you able to boil your water faster with the same temp flame? Because you had a bigger flame. You had more gas coming out of there and more flame, right? So now let's change. Let's think about this a different way. We have some amount of heat that we added. Some number of joules to your water to get it from 18 to 100 degrees. Guys, stay with me. If I had a bar of gold that had the same mass as your water, it'd be a smaller bar of gold. If I had a bar of gold and I put that on your stove also for 20 minutes or for 10 minutes, what would the temperature change be of that bar of gold? Would it change more than the temp of the water changed or less? More. How do you know? Because this number's lower. Plus, intuitively, does that kind of make sense? Does that seem like that would be the case? A gold bar versus a pot of water is kind of what I'm saying. That the temp would increase more. So we'll figure that out later. Write this down. This whole page. This is the math. I know you guys were eagerly waiting for the math. Climber, just give me the math. Done. Q is heat. Why they picked Q for heat, I do not know. But they did. M is mass. That seems like it makes sense. C is specific heat. Now that's the numbers on that big chart that you just had before. That will be given to you. You don't have to memorize all those things on that chart. And then delta T. Delta T, change in temperature in Celsius degrees. This is an important one. Delta T is the change in temp. For our boiling water example, what would our delta T be? 100?
No, it'd be, well, it starts at 18 degrees, 92. Or 80.
Take your time, work it out, Henry. You're getting so close.
82.
Third time's a charm. So yes, for our boiling water example, this would be 82 degrees. We're changing the temperature from 18 up to 100. If you started with, let's say, hot water out of your tap, right, your delta T would be less. You start with just tap water, cool tap water, you're going to start at 18, let's say. Maybe less. I don't know what your tap water temperature is. But if you started with hot water out of your tap that was coming out at, I don't know, let's say 30 degrees Celsius, then your delta T would only be 70. Right? And so with this, we can actually solve for the amount of energy it takes to boil our water. So let's do that. We're going to say 1,600 grams of water. Solve for, I will write this out. Q equals MC delta. Solve this problem. Specific heat of water. Go ahead and use 4.18. for your specific heat of water? What's that? Well, 1600 is your mass, so that's M. C is your constant. Q, that's what we're solving for, is Q. Q is the heat. What do you mean the one on the left? The variable, that's what we're solving for, is the Q. Q is the heat. Yeah, just multiply, multiply, multiply. Unit. What is our unit for Q? Joules.
Oh, so you just put
Yeah, the unit though. The unit will be joules.
4.18 in Q, right?
No. C is 4.18. What's our M? What's our mass? What's our C?
18.
Did you get it right?
Is it 18?
And what is our delta T?
4.185.
So there is a reason the unit for C is so weird. The unit for C is joules divided by grams times Celsius, degrees. That cancels out. Degrees Celsius cancels out. Grams cancels out, and you're left with joules.
Where did we get 82?
Remember, delta T. If we start at 18 degrees, what's our target temp? How much change do we want in our temperature for our water?
How are we supposed to find that?
You just
The
said
boiling temperature for water?
Oh, 100.
Bruh. Bruh. Bruh.
Why are we taking common sense as chemistry, guys?
Bruh.
18 plus 82 is 100? Is that what you're saying? Okay.
Delta T is the change. Somebody give me a number.
4.
What was it? Now, is that a big or a small number? That's pretty big. That's pretty big. I would probably accept this as, if I was going to write this down, I'd probably call this 548.4 kilojoules maybe. These are the same thing, but that number seems kind of unwieldy. Yeah, just multiply and just plug it in the formula. I would make it kilojoules. I'd move the decimal 3 points over. Yeah, either one of these would be fine. Now, if
Don't get rid of that.
No! Get out. Bro, you've been banned. What's my weekend? Don't hit me, they're both.
I feel like those like England teachers who are their
You can take your shirt.
take off my sweatshirt when it warms up. It's freezing.
solve this problem.
Okay.
Given the first problem, let's actually find out what would happen if we started with a exactly same mass of gold instead of water. We put it on in our pot, we put it on our stove, we leave it on there for however much time. but we are going to add the same amount of heat to a bar of gold. What will its final temperature be? Like 12. I'm going to guess that's incorrect. No. No. No.
It's 16.
That's not what we're saying. But the boiling point of gold is several thousand degrees Celsius.
Oh, okay. Same start temp with the same added heat. Oh, so it's the exact
So you're starting at 18 degrees and you're adding 82.
Oh.
Yes.
We just
No,
multiplied
I didn't say heat it up the same number of degrees. I said give it the same heat, the same starting temp, and the same mass.
Yeah. So we're just what are we not
You're
understanding?
solving for delta T indeed. What number do we know in this one? Same heat added. Yes, same heat added.
10.58.
No,
Okay.
not even remotely close.
If we had a bar of gold in the same
Your bar of gold got colder? You put it on the stove and your bar of gold got colder, Keegan? That doesn't make
I
sense.
guess so. I don't know.
Seems odd.
I'm not a metallic expert.
Ah. That is right.
How did you do it?
Math is correct.
Can't do like I give up all that.
Math is correct.
Just put
All right, what is our formula we're going to use here? So let's plug this in. What's our Q? It's the same heat. Look at the question. We had the same added heat as the water. That water heat was up here. That's what we solved for last time. What is our M?
16.
Same mass of gold. What was our C?
82.
What's our C for gold?
Same start.
0.129. That was given also in the question. 129 joules per gram Celsius. And what was our delta T? We don't know. That's what we're solving for. Right? So now, let's just plug this into our equation. Q is 548,416. That's a little too significant, but we'll leave it in anyway. Mass is 1,600 times C was 0.129 times delta T. How do we solve this algebra problem? Divide. Divide. Delta T equals Is this our answer though? That's change in temp. What did the question ask us for? What is the final temp? So is this the answer? No, plus our starting temp, right? 2675 degrees Celsius.
Oh my god. Guys, why do people just make up science?
If you like this kind of math and these kinds of questions, welcome to physics, ladies and gentlemen. Welcome. This is what physics is. This is a very standard looking problem in physics where it's two parts. You're taking one variable or one answer from one thing and dumping it into another. There is a ton of this sort of math in physics. So if you dig this, you just had fun in the last 10 minutes. You are going to love you some physics next year.
Why did
But this is what physics is this kind of stuff.
What did you mean by physics was gonna be a junior level class and not a sophomore?
It used to be taught to sophomores. Most of the class was sophomores was physics. Now it'll all be juniors.
I know, but why are you making it harder for me?
Because juniors will have one extra year of math under their belts that sophomores in the past did not.
My sophomore are gonna do chem instead, so I feel like you should
True.
do math for us and just let us
No.
have a sophomore level class.
So let's bring this all back in.
What's the answer on that?
So, did our gold temperature increase more or less than our water temp increase? So, the melting point of gold is something like 2,000 degrees Celsius. So, if we put the same amount of heat into the same amount of gold as we had water, the temperature increase would be significantly more. We would have a pot of molten gold. Could you drink it? It would probably be the last thing you ever had to drink. Questions on how this works? So, due first thing tomorrow,